Carlos, for the presentation.
Okay.
So we can move to the second speaker. Is Hosein Haghi. Are you ready? Let me give you.
Stop sharing.
If you just make me presenter, I can share my screen.
Yes. Okay, you are now the
Okay.
presenter. So here we are. Okay, so we start when you like. Okay.
Yeah. Do you hear me well?
Yes.
Good. So let me just. Okay. Hello, everybody. And first, I would like to thank the organizing committee for inviting me to this talk. So in this presentation, I'm going to talk about the recently reported dark matter-free ultra-diffuse galaxies, which was reported by Peter van Takkum a couple of years ago, and that they claim that these types of galaxies are problematic for modified gravity theory like Mond. And I will show how the Mond simulations can explain the dynamics of these types of galaxies. Of course, I have already planned for a more technical talk in Mond, but as I saw in the last 2 days of meeting, most of the audience are not expert in this field. So I decided to start with a long introduction in dark matter problem and also its alternative like Mond. So this is the reason that why I added this subtitle here. So I start with a longer introduction actually. So this is the outline of my talk. My talk includes 3 parts. First, I briefly explain how the idea of dark matter was raised a few decades ago, and then I will address some of its challenges in different scales. Then I'm going to explain what the theory of Mond is about and how this works theoretically. Then I will give you a brief report on our recent analysis of ultra-diffuse galaxies. Specifically, these 3 guys, DF2, DF4, and DF44. The problem is that, in general, the problem is that in astronomical scales of larger than, for example, 1 kiloparsec, like stars in a galaxies or galaxies in a galaxy clusters, the objects move very faster than what we expect from the gravity of observed matter. So the idea is to reconcile this, to reconcile galaxy scale observations. For example, for the first time, Suiki was the first one that showed the Doppler velocity of the galaxy in Coma cluster imply roughly a mass-to-light ratio of 400. And there are 2 different approaches that is suggested to explain this faster motion, either by adding some unseen mass or different law of gravity. I mean, the more gravity instead of more mass. So to give a general overview of, I wanted to begin by showing the problem that we are going to solve. And the problem is that if you plot the rotation curve of a galaxy as a function of distance from its center, then the data points are up here and show a flat rotation curve in the outer skirt. But most of the galaxy mass is within 5 kiloparsec. So beyond that, you expect a Keplerian declining in the rotation curve. This is just what happens in solar, also in solar system, where the more distant planets orbit the sun slower. So of course, as you see, this is not correct for the galaxy. So what is the reason for this? One popular explanation is dark matter halo, which is distributed around the galaxy, around the visible part of the galaxy, that can boost the rotation curve because there is still significant amount of mass beyond the baryons, which is causing this boost to rotation curve. And the main point of this finding is that many galaxies with a wide range of different sort of galaxy masses and surface brightnesses have this flat rotation curve. So this is the business of the dark matter, the rotation curves. So in this picture, then galaxies look like this. So they have the visible sort of disk. Then there is this halo of dark matter, which is shown in black. But it is important to note that the real galaxies actually, the real galaxies that we see, just baryons. There is, of course, no direct evidence for this invisible mass. And all we have is the visible disk rotating too fast compared to the standard theory. So that is the flat rotation curve problem. And the problem, of course, is caused by the application of Newtonian gravity. It is an important issue. And it is because of the application of Newtonian gravity to the distribution of detectable mass. So this is, however, raises the issue of whether the Newtonian gravity is itself correct or not. The need for dark matter halo is also proposed by these guys to explain the stability of bar in some of these galaxies. In fact, the galaxies, the galaxy disks with bar, with this bar structures are unstable without extra mass. So we need, again, some kind of halo around the galaxies to have the stable bars. And another independent evidence for dark matter comes from the gravitational lensing of galaxies and galaxy clusters. And you see here the unlensed and lensed image of background galaxies. And the interesting thing is that the amount of matter to explain the lensed image is quite consistent with what we need for the dynamics of galaxies. And also in cosmological scale, we also need dark matter to explain the large scale structures and the distribution of the structures in the universe. Indeed, the non-baryonic matter is needed to collapse earlier than the baryonic matter to form structure formation, the structure that we observe today. So yeah, we need dark matter also to explain the matter density fluctuation that we see in the cosmic microwave background radiation. And so in general, I mean, if I want to summarize, according to the standard model of cosmology, the universe basically starts with a Big Bang and a hot plasma, and we also have inflation period, and the universe expands, and today we are experiencing again a new inflationary period because of the action of dark energy. And as the universe expands, the gas cools, and the first stars and small galaxies are formed and merge to form larger galaxies. And today we would be observing the universe and these galaxies. So yeah, in the standard model of cosmology, we need dark matter particles. And of course, that are not the part of the standard model of particle physics. And we need dark energy, which is totally not understood. And also we need dark baryons, and we need dark forces, and we need inflation and some sort of fine-tuning of galaxy formation of cosmological simulations. So an important fact is that the dark matter particle still not observed despite the decades of very expensive experiments. And the dark matter hypothesis also faces very serious problems in small scales, I mean galactic scales. Here I listed some of them, but I would just briefly explain part of this list in my presentation because I don't have enough time actually. So one of these challenges is the distribution of dark matter in the center of galaxies, known as the core cost challenge or core cost problem. In fact, the dark matter only lambda CDM simulation, the halos are too costly at small radii compared to many observed galaxies. Indeed, the observed galaxy rotation curve don't follow the theoretical prediction from cosmological simulations. And so, for example, in this case, you can see in low mass or low surface brightness galaxies like this one, DDO 126, which has a well-measured rotation curves. The rotation curve shows a better fit with constant density cores at the small radii instead of the Cosby profile, for example. So to solve this problem, some solution is suggested mostly based on the effect of baryonic physics. It seems the feedback process, such as stellar wind, supernova outflow, can reduce the central density. But most of this solution works only in a range of galaxy mass. And for example, for low mass dwarf galaxies and for very high mass spirals, it doesn't work as far as I know. Now, let's see what happens in cosmological scales. They are two clusters which have collided each other and gone out again and left the gas in between, this red part. In bullet clusters, there is an offset between the X-ray, the gas distribution, and gravitating mass, which is shown here in blue, as obtained from Wick lensing. And it was argued to be a strong evidence for the existence of collisionless matter. So one important aspect of bullet cluster that was considered as a problematic is the high collision velocity. Actually, the observed velocity of galaxy cluster that is predicted to be the order of 200 kilometers per second in the CDM model, but from observation, it should be about 3,000 kilometers per second, which is too higher than expected from lambda CDM simulation. So this is a serious problem for cosmological simulation. So another challenge that I would like to address is the phase space correlation of satellite system around the galaxies. We can observe the three-dimension distribution of satellites, or better, I would say 6-dimension, because we have also the data for velocity of the satellite. So this is the picture of satellite galaxy around the Milky Way, for example. And this is what we see from observation, from cosmological simulation. Each point here is a galaxy which is orbiting around the main galaxy, the most massive galaxy in the center. And it is found in 2005 that the satellite galaxies are in a plane much like the planet around the sun. And so the question is that, is the Milky Way unique in this regard or not? And the answer is no, because the similar plane of satellite is seen in the nearby galaxy M31. And the question again is, how about the other galaxies? And for example, the Centaurus A, which is a very close group to our galaxy, it has also a large population of satellite galaxies, which is in a thin plane, which is rotating. So this proves that the Milky Way and M31 planes are not unique. And in fact, these are 3 cases. So Milky Way, Andromeda, and Centaurus A, that are the only that we know the 3D distribution. So for these 3 cases that we have the accurate data, we see all of them shows a plane of satellites. So it seems it is a rule and not just an exception. And combining the probability of such system shows a 5 sigma falsification of the dark matter models. And another important challenge is the shape of the galaxy, the morphology of galaxies. And the shape of galaxies that we observe today is inconsistent with what is expected from lambda CDM simulations. For example, in simulations, less than 10% end up in a disk form, but in observation, we see about 90% of galaxies in the form of disk. So it is a very serious challenge for lambda CDM. So yeah, after addressing these problems with lambda CDM, now we are motivated to see the alternative to dark matter. So one of the most successful alternatives to dark matter is Mond, modified Newtonian dynamics. It was developed by Milgram to address the rotation curves in 1983. By the way, only a very limited amount of data was available in 1983, and just a few high surface brightness galaxies. So similar to the Newtonian, similar to the Newton being motivated by Moon's motion, for example. The prediction of rotation curves for low surface brightness galaxies were successfully approved much later. I think it's about 1990 or 2000, I don't remember exactly. You can write a Lagrangian for Mond. One to understand is that the kinetic part of the action, this part, is not modified, which means we have standard law of inertia. And the gravitational part, this part, is modified to get this Poisson equation, this modified Poisson equation. And because this new Poisson equation is nonlinear, it breaks the strong equivalence principle. And there have some studies which actually found the strong evidence for this. So this nonlinearity makes the use of the usual Newtonian embodied simulation codes impossible in Mond regime. As a result, the internal acceleration, as a result of nonlinearity, the internal acceleration of a system with mass distribution depends on the position of another objects or host system. For example, the internal velocity dispersion of a globular cluster or dwarf galaxy depends on the gravitational potential which is induced by host galaxy, even if the external field is constant. And so this is a unique effect that we don't have any counterpart in Newtonian model in Newtonian gravity. So according to this effect in Mond, the internal gravitation of a bound system is suppressed here. By an existing external field, if it is sufficiently strong, a dwarf galaxy has weaker self-gravity when, for example, if it is in close proximity of massive hosts. So in a simple word, the external field reduces the strength of the gravitational acceleration in a system, for example. So as I said, this effect is completely unique in Mond and doesn't exist in a standard gravitational model. So it makes an important prediction for Mond and important test for Mond. And for example, in this research paper, we studied the rotation curves of a sample of spiral galaxies and showed that the external field can successfully remedy the overestimation of rotation curves in galaxies in Mond fields by decreasing the velocity in the outer part. So as I said, the external field can decrease the velocity in the outer part of the galaxy. So you see, we get a better fit if we assume the external field. And interestingly is that the amount of external field is consistent with the amount of acceleration that this galaxy, for example, experienced from the nearby galaxies. So now let's see what is the... Yeah?
Sorry, I have 5 minutes left.
Okay, that's fine. So now let's see what is the prediction of Mond for the internal dynamics of spherical system. Here, let me just skip this slide, I think, because, yeah, it's better to go to this slide. And yeah, in 2009, when I was about finishing my PhD, I calculated grids of n-body model using n-body code, which is a code developed by an Italian group in Bologna, to formulate the internal velocity dispersion of a spherical system in the intermediate region. And I found an analytical formulation for velocity dispersion as a function of external field and internal field based on the Mondian n-body simulation. So for any, so you can see here, for example, the velocity dispersion of a system in general as a function of external field in this form. So for any non-isolated system with non-external acceleration, it is possible to calculate the velocity dispersion using my formulation. And so it is important to apply this formulation for example, dwarf galaxies in a galaxy clusters. So then we apply this formulation to calculate the internal velocity dispersion of ultra-diffused galaxies. But first, let's see what is the ultra-diffused galaxies. Actually, a fundamental prediction of hierarchical galaxy formation models is that all galaxies are surrounded by a vast of complex network of ultra low surface brightness filaments and S streams, which is a result of high merger rates of the halos. So search for galaxies with low baryons content is very difficult outside the local group due to the low surface brightness. And the Dragonfly telescope array was designed by Peter van Dokkum a decade ago to probe the universe down to the very low surface level. And because their lenses have no light scattering, they can reliably get image down to 32 magnitude. That's 40 times fainter than current telescope in the world. And so they found a new class of ultra-diffuse galaxies in 2015. And since then, about 1,000 of such galaxies are discovered. So you see their typical size is about 2-3 kiloparsec, similar to the Milky Way size. But the mass is about 10 to the minus 3 times lower than the Milky Way mass. So for that reason, these systems are extremely diffuse and low acceleration system, which is a Mondian system, I mean. So here also you can see the the NGC 1052 DF2, which is in size similar to the Milky Way almost, but in mass is very smaller. And for that, the velocity of this galaxy is extremely smaller than the Milky Way. it's about 7 kilometers per second compared to 200 kilometers per second. So yeah, here is some figures of this field. This is the dragonfly field. NGC 1052 is this. And if zoom in, you can see DF2 and some other galaxies in nearby. So yeah, we try to explain the dynamics of these two objects. Yeah, let me, because of time limitation, I skip the details. Yeah, let me just show you the stellar mass. It's important to see that the stellar mass of the main galaxy, NGC 1052, is about 10 to the 11 solar mass, and the separation is about 80 kiloparsec from DF2. So we show that the external field effect of this galaxy is important for that dwarfs. And in the first report by Van Dokkum, which was published in Nature, they reported a galaxy lacking dark matter. They didn't assume the external field of this main galaxy. So they found a wrong result, that the dynamical mass to stellar mass is about 1.7. So they claim that it seems that the dynamical mass of the system is similar to the stellar mass, which means that this galaxy doesn't have any dark matter. So we wrote a BCA in Nature in this regard and showed that the claim is wrong, and there are several problems with their results and conclusions because they didn't consider the external field and ignored this very important effect of Mond. Since they didn't find, I mean, they claim that this galaxy is without dark matter, it makes a serious problem for modified gravity models like Mond, because in Mond, these systems are completely Mondian system, low acceleration, and we expect more gravity in the system, which is ineffective way we expect more dark matter actually. So in this PCA, we showed that the external field effect can play a role for these guys, and show that the dynamic, let me skip the details. Just you can see here that the velocity dispersion of this system as a function of the separation, because we don't know exactly what is the separation of DF2 from the main galaxy. We just see the projection. So actually, this is the minimum distance of these two guys. So if we change the distance, even for a very larger distance, we show that the velocity dispersion is consistent with Mond in 1 sigma level. And also we did some n-body simulation, and yeah, and just 1 year later, Van Dokkum reported the discovery of DF4 as a second galaxy lacking dark matter with very similar properties to DF2 in terms of its size and surface brightness and morphology, and distance, of course, with the velocity dispersion of about 4 kilometers per second. Again, for this case, we showed that these three main galaxies, which are listed here, NGC, I mean, yeah, the DF4 is near to these three galaxies, NGC 1035, 1042, and 1052. And assuming the external field effect of these galaxies can reduce the velocity dispersion of this galaxy to be consistent with the observed value. So again, we showed that these systems are consistent with Mond. So yeah, I would stop here with my conclusion. actually we provide analytic formulation to take the external field effect into account to estimate the dynamical mass of non-isolated system. And we showed that the dynamics of DF2 and DF4 is pretty consistent with Mond prediction. And yeah, that's it. Thank you.
Thank you. Thank you. So maybe we have time for one short question and short answer. If there is any question.
Could I ask a question, Jorge?
Please.
I remember that when, let us say, people discovered bullet cluster and claim that is direct evidence for dark matter, Mond people said that they could fit observational data with Mond theory, but they introduce neutrino mass around 2 eV. What about recent progress in this direction? I mean, to fit observational data for bullet cluster with Mond. Because it looks very heavy, neutrino mass. 2 EV is too much now.
Yeah, exactly. Yeah. Yeah, in 2007, I think Gary Angosh in St. Andrew, I mean, in a research paper showed that the stereo neutrino can reconcile the bullet cluster with Mond. And recently, in other case, El Gordo, Elena Asensio and Indranil Banik and Pavel Krupa and University of Bonn, they showed also that the El Gordo case is also compatible with Mond if we introduce the neutrino, stereo neutrino as a collisionless matter, which is, I mean, not assumed to be dark matter, of course. It's a completely normal particle that we expect in standard model of particle physics. Yeah, of course, without stereo neutrino, it is difficult to explain this observation in Mond.
Thank you. Thank you, Haghi. So thank you again for your presentation. And so we can move to the next speaker that I see already. Hi, Clement.
Question out of my talking time.
Sorry?
Can I borrow 30 seconds of my time to ask a question?
Yes, okay. Okay.
Okay. Yeah, so thank you, Hossein, for the presentation. You say your analytical estimates that you derive during your PhD are spherical. You know, you have the spherical symmetry approximation, but as far as I know, galaxies are not, most of galaxies are not spherical. So isn't it a spherical problem, or do you have, you know, correction to the sphericity, or where do you stand here?
Yeah, on that time, it was the only way that one can assume the external field effect. And I used that formulation just for a spherical system, like globular clusters and dwarf spheroidal galaxies. It is not possible to use that formulation for example, a spiral galaxy. But now we have some embodied simulation code like Phantom of Ramses that can do a realistic simulation and implement the external field effect for this.
And Phantom of Ramses agrees, I guess, with your analytical estimate.
Yeah.
Very well. Thanks. Good, then I just had time to set up in the meantime. Should I start, Jorge?
Yes,
Right.
you can start, please. Please go ahead when you're ready.
Okay. Well, so thank you for the invitation. Welcome to my talk.